Hello and welcome to our talk on optimization for the direct shadows for Unreal Engine 5. Today, my name is Peter Sikachev. I'm a technical director at Virtuos Warsaw. Together with me, the co-presenters are Ihor Pavlovsky and Ostap Trush, who are graphics programmers at Virtuos. And let's get started. Here is the outline of our presentation. We will start with a short introduction, after which I will pass the mic to Ihor, who will tell you about the issues there are with directional shadows in Unreal with virtual shadow maps. Then he will describe our proposed time slicing solution. We will then do a short demonstration on the valley on the ancients, after which Ostap will describe our solution to the world position offset geometry and provide you describe how we solve the implementation challenges that we had along the line. He will also describe the performance gains, and we will finish with more demos. So we will be presenting our results here on Valley of the Ancients map, but we will also provide you with the performance gains we got on our not yet announced titles on Xbox One X. So let's start with an introduction. We are here in Virtuos Warsaw. We are part of the Virtuos Corporation that houses over 3,700 developers spread over 22 locations. And over the last 20 years, we helped ship in over 1,500 titles. So I will move into how we started working on improving something in Unreal. So that was a part of our cross-studio collaboration. So this is something that we really enjoy doing at Virtuos because it allows us to tap into the resources that may be locally unavailable and reach out to other studios. So one of our studios was working on a full cycle development title, meaning they handled the whole production in-house. This is one of the type of the works we do. Besides of that, we also do co-development, we work on internal IPs, and so on. And importantly for our case study here is that this was an open world game with a dynamic day-night cycle. So those are type of the titles that would benefit the most from the optimization that we propose. At that, I'm passing the mic to Ihor. So Ihor, take it away.
Okay, can I have like slide switcher?
Yes.
Thank you. So, to begin with, we started our research due to Unreal Engine 5 default implementation lacks configuration for virtual shadow maps clip map rendering. What this means is that the engine renders the entire clip map in a single frame without the option to distribute the workload. Any movement of a directional light source, even slight, triggers a complete invalidation of the whole clip map. This means that all visible tiles within the virtual shadow map of each clip level must be re-rendered. In scenarios like a day-night cycle, when sun's position constantly changes, this continuous re-rendering can severely impact performance. Currently, the only way to mitigate this issue is to update sun's position less frequently, such as once every n frames. But unfortunately, this approach introduces noticeable spikes in frame time when sun's position does update, leading to a less smooth visual experience. Oh, sorry. Okay. Yeah, sorry, it doesn't switch. Yes. Yes, and in this video you can see an actual scene along with the debug visualization that reveals whether each tile within the virtual shadow map of each clip level is cached or not. Green color means that the tile is cached and red that it's not. Initially, the sun was not moving, thus all tiles were cached. But as soon as the sun began to move, all tiles became invalid, thus forcing the engine to re-render all the shadows. And now moving to our proposed solution. Time-sliced clip map updating. So, instead of updating the whole clip map every frame, we can use time slicing instead for better performance. This involves updating only a portion from the total number of clip levels per frame, such as 2, 3 or more if needed, and the remaining levels would stay cached until the designated update time. This approach introduces only a small manageable loss in visual quality if update cycle is not spread across too many frames. Moreover, the degree of quality loss depends on day length, as longer in-game days allow for smoother transitions, and sun's position, because changes in shadow position are more pronounced when the sun is closer to horizon, due to cosine relationship between the angle of incoming light and shadow movement. So, taking this into account allows to achieve visually pleasant results with appropriate configuration. And now, if you input and paste places from the code to give you better insight into the design. So, F virtual shadow map per light cache entry. An instance of this class corresponds to each light source on the scene, and this relation is managed by another manager class. F clip map cache key is a member of F virtual shadow map per light cache entry class, and it holds information about origin, position, and shadows projection of clip levels. Originally, all clip levels shared the identical data since they were updated simultaneously, but our optimization modifies this so we can track these changes independently for each clip level. Therefore, you can see that all fields of F clip map cache key structure are arrays of size equal to maximum number of clip levels in clip map. We use an array of arrays to group indices that need updating within the specific frames. For example, during frame 0, we update clip levels with indices 0 to 3, during frame 1, 4 to 6, then 7 to 9, and so on. This allows us to selectively invalidate only the necessary clip levels, as you can see in the update clip map method. The for each loop goes through the predetermined set of indices and sets clip map cache key B light direction changed flag to a corresponding value for each clip level. Each frame, an instance of F virtual shadow map clip map is created in the main rendering loop. During its construction, the necessary values are calculated to populate F clip map cache key structure for the given light source. This data will be later used to determine view projection matrices and whether new virtual shadow map tiles allocations are required due to camera movement or any other factor. Additionally, a virtual shadow map clip map constructor calls update clip map method that was shown in the previous frame. As you remember, this method can mark clip levels as completely invalid, thus forcing a re-render of them. So, in the first image, you can see a reference to F clip map cache key structure is acquired from manager class for the given light source. All per clip level data, such as light direction, is stored within this reference structure. Then in the second image, update clip map method is called. And in the third image, there is only part of the calculations, but it may clearly demonstrate the idea of separately treating data for each clip level. This allows clip levels that are not updating during this frame to remain with correct data to match their shadow maps. that were cached previously. So, all the configuration is performed via properties of an actor that represents directional light source on the scene. As you can see in the first, probably you can see, is it possible to move a little a window with Ostap? Thank you a lot. It's only temporarily. So, as you can see in the first image, with our implementation, it's possible to configure whether to enable time slicing for each directional light source separately. And here we also set indices of clip levels to update during specific frames. The length of a full update cycle is directly controlled by the number of clip levels indices groups, such that each group corresponds to one frame. And moreover, this implementation is completely compatible with already existing Unreal Engine 5 projects, as our code does not conflict with any default features of Unreal Engine and only allow to optionally enable time slicing for chosen light sources. And now moving to demonstrations. So, in this video, you can see the algorithm in action, configured to update one clip level per frame. Despite the sun is moving pretty fast, as you see, visual artifacts are almost not visible, and they will be seen even less if the sun moves a little slower. On the top left corner, you can see how invalidations are processed by the algorithm, clip level by clip level. On this slide, you can see the entire configuring process of time slicing in Unreal Engine. It takes less than 3 minutes, but the video is sped up to passing 30 seconds. Essentially, all you have to do is tick the box to enable time slicing for the chosen light source, and then manually distribute which clip level synthesis to update during which frames. You can even repeat the same indices during the same update cycle if there are any clip levels that need to be extra smooth. So you update them several times during the same update cycle. This gives flexibility to developers and allow to configure time slicing for specific needs of the project. Okay, and I'm passing microphone to Ostap to tell you more about world position offset time slicing.
Thank you, Ihor. So one of the biggest limitations of regular time slicing is geometry with world position offset. That is because that geometry is re-rendered every frame into the shadow pages, which are dynamic, which are essentially the pages which clear their contents at the beginning of every frame. And even though such geometry does have movements, they are not visible enough when the camera flies far away from such geometry. For this reason, we can neglect some of those movements that happen every frame and render the geometry into the static pages in Unreal Engine, and then let the time slicing algorithm pick up the rest. Next slide, please. So here on the demonstration, you can see the time sliced world position offset enabled to the left and the time slicing disabled to the right. And you can clearly see that the geometry starts lagging when the time sliced world position offset is enabled. That is what we want. And even though you see it visible when you're looking at it up close, in scenes that have a lot of time sliced, a lot of world position offset geometry, like a lot of trees and bushes in the forest, these lags in shadows won't be visible. However, you will heavily save on the shadow computation time. Next slide, please. And here you can see the same implementation and the same scene, however, with the debug visualization applied in the Unreal Engine. And you can see that the time-sliced world position offset implementation completely disables the blue dynamic shadow pages, which are re-rendered every frame, which is exactly what we need. And it only leaves the green cached shadow pages and the red uncached shadow pages, which clearly allows time slicing to work absolutely correctly. And also should be noted that the current implementation of time-sliced world position offset works only for the nanite geometry, meaning that non-nanite geometry with world position offset won't work with time slicing as of now. However, the regular time slicing works with both nanite and non-nanite geometry. Next slide, please. So before we look at the performance gains, it's worth covering problems that we stumbled upon during the development of our optimization. By far, the biggest problem was how the clip map levels are defined and picked in the default Unreal Engine. The default Unreal Engine, as you can see on the top left image, while having a clip map level radius, it fills that radius with shadow map pages. And in that way, it defined the edge of a clip map level where those pages that fill the clip map level radius are ending. Meaning that on the top left image, you can see that we have two clip map levels, the yellow one and the blue one. And you can clearly see that where the yellow clip map level ends, it's not circular and it's has its edges as a respective shadow map pages. However, that is a problem for time slicing because the actual Unreal Engine implementation of clip map levels moves all of the shadow pages projections all at the same time for all clip map levels, which is, as Ihor mentioned before, not what time slicing does. And that's why when we try to do the same thing but with time slicing enabled, you'll see a case that you have on the top right image on your screen, which shows us that if the projections get updated for one clip map level but don't get updated for the next, we'll see a mismatch in projections, meaning that Unreal will simply won't know what clip map level to pick for the red regions that you can see on your screen. And the solution for it is pretty simple. We just pick a clip map level not based on where the shadow map pages that cover a clip map level radius are ending, but simply on the clip map level radius. This removes the problem with the clip map shadow pages projection and removes all the artifacts that come with it. Next slide, please. Now let's review the performance gains for the time slicing technique. We will first look at the gains for the Valley of the Ancient Unreal Engine 5 demo, and then review the gains for an undisclosed AAA release that we battle tested the time slicing technique on. So here's the testing setup for the Valley of the Ancient. We have two scenes. The first scene is basically a scene with a ton of the night geometry on the screen, and the second scene is a more like real in-game scene where you see the player and you see a little bit of geometry. We have prepared the two algorithms for time slicing. Both are of a 9-frame length. The first one is a linear one, which starts essentially from the lowest clip map level to the highest clip map level. The second one is the symmetric one, which basically combines the smallest and the highest clip map levels until it all converges in the center. And the PC specs you can see right here on the screen: an RTX 4070, Core i7, and 64 gigabytes of RAM. It's also worth noting that we have added a day-night cycle to a Valley of the Ancient demo, as it's not there by default. So let's review the tests for scene 1. As for the baseline test, we get 6.7 milliseconds for shadow computation every frame when the sun is at zenith, and 6 milliseconds when the sun is at horizon due to less objects casting shadows. So our symmetric algorithm gives the biggest spike in 9 frames as 2.7 milliseconds at zenith and 2.6 milliseconds at horizon, with 6 out of 9 frames falling in the range between 1 and 2 milliseconds, and 2 out of 9 frames exceeding 2 milliseconds. All of the other frames fell in the range in less than 1 millisecond for shadow computation. The linear algorithm is pretty similar. For Venice, we have 2.8 and 1.9 milliseconds for Venice and Horizon respectively. And we have 5 out of 9 frames fall in the range of 1 and 2 milliseconds, and 2 out of 9 frames exceed 2 milliseconds, and then all of the other frames took less time than 1 millisecond. So as you can see, the gains are pretty apparent, and based on this single scene, the gains in shadow computations are between 50 and 70% on a general scene that has a fair amount of the night geometry in it. Next slide, please. So at the scene 2, it has less night geometry and more non-night geometry, like a player skeletal mesh. As a baseline test, we get 4.3 seconds at Venice and 2.5 seconds at Horizon for shadow computation. The symmetric algorithm cuts it down nearly in half to 1.4 for both Venice and Horizon, and only 3 out of 9 frames fell in the range of more than 1 millisecond and less than the spike, and all of the other frames fell in the range of less than 1 millisecond. And for linear algorithm, the results are a bit worse, 2.5 and 2.5 for both Venice and Horizon, and generally the frame distributions are again worse, as you can see on the screen, with 2 out of 9 frames falling in the range of 2 milliseconds and all of the other frames taking less than 2 milliseconds. Based on these results, the shadow computations are between 40 and 68% on essentially a typical game scene with a player. So now the previous scenes did not have any world position offset geometry in them, but we still need to test our implementation of world position offset time slicing. So we handcrafted a custom scene. Essentially, as you can see, it's pretty simple. It's an NI tree with around 350,000 triangles and around 600 trees laid out in the following grid. The algorithm is bottom to top, 17 frames. You can see on screen how it works. And the PC specs stayed the same. And here are the results of the performance tests on that scene. As you can see, the world position offset is enabled to the left. And here we compare not only the shadow depth pass that the Unreal Engine has, as we did in the previous tests, but also we compare the build page allocation pass, which essentially is an Unreal's preparation for rendering shadows. And as you can see on these results, if we account for build page allocations, we get 49 to 50% gain in shadow computations. And if we just cut them and don't account for shadow depth, we get around 81 to 90% of gain in computations only on shadow depth. And it also should be noted that build page allocations takes longer with world position offset, essentially because here we showcase the worst case scenario for the world position offset time slicing. So in reality, on an average scene, the average gains with build page allocations could be even greater. Next slide, please. And now let's review the time slicing gains on an unannounced AAA release. Generally, we have 4 scenes for such a test. The first scene is a flying camera that has a view over the city. The second scene is a player POV and the view in that city. And the 2 other scenes are for world position offset mostly. Scene 3 is flying camera with a view over a forest with world position offset. And the last scene is the player POV with a view in that forest exactly. So as you can see here, we have 3 main columns. The first column is where everything is off. All of the optimization are off. We are operating from default Unreal here. The second column is the time slicing is on, but the world position offset time slicing is off. And the third column is both the time slicing and the world position offset time slicing are on. And unfortunately, we don't have the spike data for this column. And so let's go over it. The first scene, which is again flying camera and view over the city, with all of the optimization of ours, we have a 16% gain for a shadow depth pass on average and 30% gain on spikes. For scene 2, we have 23% gain on average and only 8% on spikes. And for the scenes with world position offset time slicing, we have 19% gain on average and 10% gain on spikes. And for the scene 4, which is the player POV in the forest, we have a 49% gain on average and 13% gain on spikes. And also, I did not mention the hardware that we tested it on was Xbox Series X. Next slide, please. So based on these tests, the potential gains in shadow computations are up to 70% depending on the scene, especially if that scene has autonomous night geometry. And the gains were up to 49% on a scene from a real project. It should also be noted that the frame distribution configurations may not be optimal, and with better configurations, the gains can be even greater and more consistent. And at the end of the day, it's all really dependent on the scene and how shadow heavy for computations that the scene really is. Next slide, please. And now I pass the word back to Ihor for more demonstrations.
And yeah, here we have a few more demonstrations. It's the same volley of the ancient scene. The algorithm is configured to update one clip level per frame, and the day now is 30 minutes long. So, as you can see, in general, shadow movement is smooth enough. And if we look in close distance, there are no visible discontinuities between shadows of different clip levels. And now, let's take a look at shadows on sunset. Because when the sun is getting closer to horizon, the shadow movement is becoming more jagged, as expected. But in real case scenario, oh, it's not working yet. Oh, fine. So yes, as sun getting closer to horizon, shadow movement becomes more jagged, as expected. But in real case scenarios, this can be easily avoided by tweaking the number of indices groups, such that when the sun is low, we have fewer groups and the whole clip map is simply updated in fewer frames. Yeah, and here we have like 10 seconds when the shadows are getting longer, so...
So basically, we can load balance this algorithm, for instance, at the horizon when there is more occlusion. There is generally less need. Shadows perform better when the occlusion kicks in. So we can update the VSM faster in that case scenario. And also what we're showing here, this is pretty much extreme day-night cycle. So in reality, there are certain steps that you can take.
And moreover, I probably forgot to mention what's important, that this clip maps indices to update during specific frames can be changed in runtime. So that's not a problem to make it dynamic and have more time, more frames to update the whole clip map during the day and less when the sun is low. And now passing the microphone to Peter.
So basically, with this, we developed originally this optimization for our full cycle production title, but we are very open to sharing it and helping your game ship with it should you be interested. So reach out to us while we are here at Digital Dragons, or just follow up by email. And the way we work with Virtuous, we basically we have a team of experienced engineers that already did it on another title, which will be supervised by a technical director. And besides of that, we are of course not limited to only shadow optimizations or Unreal Engine per se. We have experience with in-house engines as well as we can provide a comprehensive technical art support. Before we finish, I would like to say a few thanks. First goes to the team in Paris that helped us testing this tech on a real title and provide us valuable feedback. Next goes to marketing team for proofreading and slide layout in this presentation. And last but not least, for Maciek, which is present here, for coordinating our efforts. Frankly, never had a producer helping on presentation before. That was very, very much welcome. And for communication with the DD organizational team. And of course, thank you so much for accommodating our needs and having one of our presenters being able to present remotely. And if you want to have some cool, want to work conversely on some cool stuff like this, I don't know how you read this, then we are hiring. So again, meet us at our booth, catch us while we are here, or visit virtuousgames.com/career. And on that note, let's finish the presentation and leave some room for questions. Thank you very much.
Thank you for the presentation, Vladimir Trubilov. So I wanted to ask, where to begin? The first one, with slicing. So the scene didn't feature any tall buildings at the horizon or far distance. And the question is, what will happen if I will have, for example, radio tower with rotating antenna, and the shadow need to be updated pretty frequent, and we will have the slicing turned on. So what we will do in this case?
So in that case, basically any, by default, Unreal places any pages that will have this rotating antenna will be marked as dynamic pages, and they will get invalidated. But if this is world offset geometry, you have a choice basically to sacrifice some quality of the update and just mark it as you don't need to update it. So the choice is yours, basically, whether you want to have a bit more performance or you want to keep the same quality.
Okay, thank you. So in case of VPO, I can just switch off the second part of optimization and we'll be fine. The second question is about fast scene validation, like if I will move camera in direction like opposite to the viewing, and the whole shadow map will be invalidated. So will we have spike?
The whole shadow map doesn't get invalidated when you move the camera because you still have like the you still have the pages from the from the previous frame. I think Unreal will invalidate if you have a camera jump, then you will have something, but you will need to handle this. Otherwise, you I think we did some camera flyovers, and there wasn't any full map invalidation every time we move the camera.
Yes, but the scene can change significantly while we don't see it.
I mean, if the scene changes, that would mean that you will have like dynamic pages that will get invalidated. Correct me if I'm wrong, Ihor, but Unreal doesn't only update the shadow, like the shadow maps that are only visible, right?
Yeah, that's correct.
Okay. So, and regarding this VPO stuff, you featured in for foliage, and it's known that foliage is pretty heavy with VSM. So have you considered anything like keeping foliage in traditional CSM?
So basically on the title that we've been working on, they decided to use nanite for foliage. Their test shown that that was the fastest way. So therefore, we mainly did it for we did the test like for We use VPO like VPO offset for nanite geometry, and then we just for foliage that is far away we don't update the VSM slices. We didn't necessarily wanted to keep two different solutions, CSM and VSM. If it's the smaller foliage like grass, then it's I believe it's better, and you will get higher quality results if you use screen space shadows for that one. Using two solutions like CSM and VSM. I'm not sure if Unreal supports using two at the same time out of the box. Maybe changes could be made. But having two different solutions, it's not a great engineering decision, in my opinion.
I see, thank you. And one more thing related to this foliage. So have you tried to do the slicing thing as you made for static pages, but for dynamic ones? So instead of doing all the, making all the dynamic things into static pages, just update dynamic one less frequent.
Yeah, but it makes not a lot of sense, because if we want to split, we just make pages static and update them from time to time. And in this case, we're remaining with dynamic pages that are updated each frame. So we have an option to update by slicing, or we have dynamic pages in case you want to update something frequently.
Yeah, but it will have benefit that you can update it detached from the whole update of the static pages. So you can have different frequency of updating for the geometry and for the static pages.
Yeah, okay, I understand. No, we haven't yet did that. Probably it can be useful, but for now we are limited to static pages in this implementation.
Okay, thank you.
That's a good idea for the future, enhancing the technique. Good one.
I don't have any questions, thank you.
So before we continue with more questions, let me just mention that the QR code that you can see now, you can scan with your app, with the Digital Dragon app, so you can share your opinion about the presentation.
Give us some hate on Twitter, guys.
Hey, yeah, quick question. So, meaning there's a lot of spatial approaches regarding frequency and whatnot. Have you considered temporal approaches as well, like these specific tiles, trying to address them that way?
Can you a little bit elaborate on your idea?
Yeah, meaning for these specific tiles, just because something's moving doesn't mean it always translates into visual significance, right? And maybe tracking this on a temporal basis between frames that hey, I don't know, the variance is changing quite significantly between frames or something like that. So let's put emphasis on these frames over others. You mentioned load bearing, so I figured this would be, I don't know, I was just curious if it was something you've investigated.
We didn't get into that. I can have a very abusive answer that we have artists for that. Basically, they need to decide whether it's moving too fast or not. I guess it is possible to come up with some heuristic that would decide whether we need to evaluate it or not. But it would be, I guess, if I'm thinking out loud, I wonder how much more performance you need to dedicate it, or you just statically analyze it before the game and decide for that asset whether it needs to be static or dynamic. So. I guess that's a possible avenue. I will be a bit hesitant to do any more analysis on runtime, because we are operating on very thin margins here.
Gotcha. Thanks.
Thank you. Great talk. I was immediately thinking about one more optimization. So when you're switching between steps, there's visibility how shadow jumps from one place to another. So the more often you update, the less visible effect is. But I was thinking maybe it would be reasonable to have a previous step and current step of the shadows and then interpolate those. I'm not sure whether it will be optimal in memory, but maybe it will reduce effect and just have interpolated shadow appearing and probably have it possible to have even less, even farther jumps. You know.
We considered we actually considered that at the very early stage, not entirely for that one, but basically to be able to have previous and current matrices for for the time slices. And unfortunately, like the title that we were working on, it was very memory limited, and we were not allowed to basically duplicate a shadow map or grow it to some extent, so we could have some tiles from previous and current frame. I mean, probably you could do it not for all tiles, but duplicating the whole VSM in memory, at least for that tile, that would be too prohibitive for the memory.
Okay, thank you.
No worry, thank you.
I have a question. Have you guys maybe experiment a little with a non-uniform clip step? So you have like more refresh closer to the camera and less refresh far from the camera?
Basically, Ostap was talking about that. The idea is that you simply set indices for each frame. So you can choose like index from 0, 1, 2, 3 for frame 1. And then for each next frame, you simply choose by one index. So you have you are updating 3 clip levels in one frame, and then level by level in one frame. And you can even repeat those indices. So if you want like extra smooth levels close to player, you simply set those indices 0, 1, 2 every frame, and add to them one index for each next clip level.
Okay, thank you.
It. Thank you again, guys. Feel free to catch us after the talk, and have a great rest of the conference.